Welcome back to Automatic Control Systems. I am Kalyana Vilvolu and I will actually resume with this lecture. In the last class, we discussed on modeling of physical systems. From this part, we are going into a new domain, new part of automatic control. This is what we call analysis. Once you develop a model, we need to analyze about the system, analyze about the model. So when I say analysis, we are looking at the performance. Performance is something what we called quantified measure. Means when I have two systems, how can I say one system is good, one system is bad, something like that. We're going to actually analyze the system with various test signals like test inputs, and then we're going to actually develop some analysis tools and also standard procedures for first and second order systems. So this is a first part of time domain analysis. So in this lecture, we are going to learn about our basic test signals. Test signals are like the signals that help us to test the system performance, or how we can analyze the system properties, system characteristics. Then we are going to actually analyze on the next part is responses of first and second order systems. The first and second order systems form the core part of our automatic control systems. In this automatic control systems lecture, we only analyze first and second order systems. We don't analyze third order, fourth order, fifth order, sixth order systems. The reason is we're going to learn that later that even the higher order systems can be approximated as second order systems. Now the time domain. So what is analysis is, we take a system, we provide some kind of test signal or input to the system, and the system is evaluated based on its output. So when you get the output, we're going to compare our input and output and then analyze how good the system performance is. So what are these test signals? Some of them you already know. We know that some of the signals or test signals are impulse, step, parabolic function, sinusoidal functions. Step, ramp and parabolic functions are time domain functions, and the sinusoidal function is a frequency domain, which we will actually discuss at the end of automatic control. So in this lecture, we are going to focus on step, ramp and parabolic functions. Suppose we are looking at a stable system. Now the word stable is analyzed here. When I say stable, where the system doesn't give or explode, or where the output goes beyond certain limits. So we only work on stable systems, and what are unstable systems we're going to learn in the later class in the analysis. For the time being, we're going to only focus on stable systems, and when we provide an input to the system, the output response has two parts. One is called a transient, one is called steady state. So if you actually notice, if anyone notice any motion aspects of a system, when you apply a change, every system tries to settle in this way. So if we disrupt some system, because of the disturbance input or disturbance, system oscillates between two states and finally settles. This part of the state where the system tries to settle or what we call the transient part of the system, and when the system settles, we call the steady state part of the system. Both these states exist in every response. If you are using an elevator, when elevator stops, moves from one floor to another floor and stops, it makes a slight vibration. This is what we call transient response. When system changes its state, every system opposes the change. So this transient behavior is because of the opposition, and this is the reason why we see this kind of transient changes in every system. So, in many systems, the steady state response, we want the steady state response to follow the step input. The transient part, we want to keep it to as small as possible. We want the transient part to die quickly. If you remember your experience in a lift elevator, when the elevator moves from one floor and stops, it makes some light vibration and stops. This small vibration we call the transient response, and when it comes to rest and stops, this is what we call steady state. The transient response only lasts from few seconds to maybe a minute depending on the application, and the transient response dies and then the system settles. This is what we call steady state. In the later part, we are going to study these two aspects. So, every system, when we apply an input or when we apply some kind of force, mechanical input or electrical input, the output changes, and the change in the output actually shows both the transient and the steady state. Before, I want to actually explain you about test signal. In the next slide, we are going to actually analyze or learn about what is performance, what is tests, or what kind of inputs. Suppose you have two cars here. Let's say one is a Ferrari, which is very popular. I think most of you know it's one of the most expensive cars. And the second one, I just choose a simple Kia Picanto, very economical, also very popular, because this gives you a big mileage. That means for 1 liter you get 15-16 kilometers of mileage, and whereas Ferrari probably you get only a few kilometers of mileage. Obviously, Ferrari is not about economy, it's more about performance. So, if I ask anyone which is a good performing car, everyone tells Ferrari. How? How do you say Ferrari has a good performance? If you are looking at the time domain performance, if you are looking at the analysis here, there is one common test that is normally conducted for all these cars. Everyone, when they sell a car, they tell you this car can accelerate from 0 to 100 in a few seconds. This car has an acceleration. Now, I want to actually show you this one. And this is a Ferrari. This is the 100 kilometer speed line, and then in the x-axis I have the time and you have the speed in the y-axis. So, if you see here, when I actually press the accelerator for the Ferrari, the speed increases, right. In 3 seconds, the Ferrari can beat the 100 kilometers per hour mark. So, we can say that the Ferrari can accelerate very fast because of big engine, whatever, you can see the acceleration. Now, if you take a Kia Picanto, it actually takes more than 12 seconds, 100 kilometers per hour. The same 100 kilometers per hour, this car takes almost 12 seconds. Now, if you are comparing this one, these two, this is a very popular test. And now, if you compare, you can say that the Ferrari approaches the 100 kilometers earlier, and this one takes a bit more time. Now, what is this one? This is what we call a simple step test. I apply a step signal. What is a step signal? The step is 100 kilometers per hour, and when I accelerate the car takes 3 seconds to approach the 100. Then the error becomes 0. This is what we call the transient part, and this is what is steady state. The error here for a Ferrari is very small, but if you actually find the error between 100 kilometers and the output speed, you get a huge error for a Kia Picanto. So, when I choose the performance in terms of the acceleration, Ferrari provides me with a good performance. So, this is what we call performance. Performance something is quantifiable. That means I can take the error between the input. The input is 100 kilometers per hour. That is the reference speed. I provide the reference to the Ferrari is 100 kilometers per hour, and then I give it 3 seconds. It gives me the output in this way. The output input relationship tries to tell that. What is the error? Input minus output. If we mark the error, I am going to get different graphs. For a Ferrari, if I actually find the input minus output, so if I actually try to calculate the error, how does the error look? So, the error actually looks into this way for a Ferrari, and if you are looking at the Kia Morning, the error graph is something bigger. So, if you compare both this error is very small. So, this error is very small, but the other error is quite very big. So, if you can see, this error is quite large. So, that is why we can, based on the error dynamics, the error, we can actually explain that Ferrari performs really well compared to a Kia Picanto. And as I said, this is what we call a step signal. So, we call this one step signal because we apply 100 kilometers per hour step input. We say this is a reference input to both the cars, and both the car provide an output that actually gives us this kind of output depending on the functioning of the car. Different cars will give you different output. So, as we analyze the performance of these two cars, we can actually now analyze our various step signals. Now, a step signal is what we actually analyzed just now. We applied to analyze the performance of two cars. The step input is a constant. So, it has no value before t less than 0. After t greater than 0, it has a constant value. The step can be a unit value, 5, 10, anything the step can be. A unit step means single unit value 1. The other class of input is what called impulse function. R of t is equal to a delta of t, where a is constant. The impulse function is a single impulse, unit impulse. Ideal impulse only has 0 width and a unit length. So, the impulses, theoretical impulse and practical impulses are slightly different, but what is an impulse in real world is what you see, the hump, the road hump. The road humps are very popular for speed control. Depending on the required speed limit, the size of the hump, the width of the hump, the height of the hump changes. That means that is an impulse, that is a practical impulse. It induces huge energy into your suspension system. If people drive very fast on a hump, your car may jump and it may permanently damage your suspension. It costs a lot of money, and that is why you have humps. Humps are there to make your speed become low, but most people have no idea what happens with the humps. They actually spoil your suspension and it costs a lot of money. The impulse function is actually modeled as R of t is equal to a delta of t. There are two other popular functions, what we call ramp and parabolic function. Ramp function is like a constant slope, and this function also is 0 for t less than 0. For t greater than 0, you have R of t is equal to a t u of t with a slope a. Parabolic function is a parabola. It also function is also for t less than 0 is 0. For t greater than 0 is a t square u of t. Now, if you observe all these functions only exist for t greater than 0. For t less than 0, all this value of 0. Why is the main reason? For real systems, we can't go back in time. So, for all practical systems, analysis is only from this instant t equal to 0 into the forward directions. We can't really go backwards into the past, so it is no meaning to actually analyze for t less than 0. So, all our test signals we analyze for t greater than 0. So, first stage we actually we are going to analyze on first order systems. So, the first one is the time response of a first order system. So, what is the time response? Is when we provide an input to a first order system, how does the behavior exist? Now, look at this nice first order system. that is modeled as RER 1 by tau s into y. This model is what we call a standard first order system, because why is a first order? Because the order of s is 1. What we have, the transfer function is R 1 by tau s plus 1 y. Because the order of s is equal to 1, we have a first order system. Generally, the first order systems represent RC circuit, thermal system, pneumatic systems, etc. So, first order systems are also very popular. We generally have a lot of systems, they are first order systems. Now, have a look at this circuit. When you look at this circuit here, the input is voltage I, output is V0. And if you try to recollect, this is a circuit for low pass filter, or what we call RC circuit. This is an electrical circuit, but we can also assume as a system as we modeled earlier. Vi is the input, output is Vo. So, if I start to the modeling, I can simply formulate the electrical equation and then make the circuit. I get the transfer function output by input y of s by r of s is equal to 1 by tau s plus r, where tau is equal to RC. Now, if you look at this model, tau is the single constant. First order system, we only have one constant that is tau. When I modify the tau, the system properties changes. For different R and C, filter time constant, you have different filter characteristics. So, if I change R or C, RC changes. So, as long as the tau is same, 1 by Ts plus 1, the model will remain the same. So, this is a nice first order system. For this first order system, I would like to analyze the unit step response. Unit step is what happens if I apply a step input to the system. How is the performance? How is the performance for the system? Now, take input R of t, that is equal to u of t. You have R of s equal to 1 by s. So, in the Laplace transform, in the Laplace domain, so our input in time domain is u of t. So, apply Laplace transform, you get R of s equal to 1 by s, and y of s equal to transfer function output, transfer function into the input, because output by input is equal to transfer function, output is equal to 1 by tau s plus 1 into 1 by s. So, you know this one we have to use inverse Laplace transform. So, I break it into partial fractions. So, I break it to partial fractions and then apply inverse Laplace transform. 1 by s inverse Laplace transform is 1 by t s tau s plus t, we get e power minus t by tau. So, using that equation, we can actually get the output is 1 minus e power minus t by tau. Now, what is input? Input is a unit steps input. So, unit step is just one value, and what is output is 1 minus e power minus t. What is e power minus t? E power minus t is an exponentially decreasing function, So, 1 minus e power minus t will be an exponential function, starts at 0 and goes to 1. So, the output you can see here is starts at 0 and goes to 1. So, if we analyze the rest, compare the input and the output, we can analyze the performance. So, now the one of the factors is we want to analyze the slope. The slope at t equal to 0, the slope of the output is the exponential curve. We take the slope dy by dt at t equal to 0. If we analyze for the y, I get 1 by tau. What is 1 by tau? Is a time constant. So, this is a constant that actually if you analyze the system, tau is equal to RC. So, different filters will have different performance. So, when you change R and C, the characters also change. Next, error. What is error? Error is defined as input minus output. In our case, R of t minus y of t. So, in our case, reference is 1, unit step input, and output is 1 minus e power minus t by tau. So, if we actually do that, I get e power minus t by tau. So, this is the error dynamics. So, this error dynamics helps us to analyze what is the behavior of the system. So, if you analyze the difference between the reference and the output, what we have is e power minus t by tau, and this e power minus t by tau changes with the system. When I say change with the system is when the time constant changes. For different systems you have different time constant. For different time constants will result in different error dynamics. So, the steady state error is when t tends to infinity, or when the time is large enough, we call the steady state. After a long time, what happens to this error? When t increases, e power minus t by 2 becomes small value. So, we call this steady state error equal to 0. That means after a long time, the output matches with the input, or the output becomes equal to the input. So, this is what we call the performance, or we call the time domain analysis. So, we analyze this, we take the step input, we convert into Laplace domain, and then we analyze the time domain output response and analyze its characteristics for unit step response. Next is unit ramp. Similarly, for the same first order system, if I choose r of t is equal to t, t is an increasing value, r of s will become, a Laplace domain will be 1 by s square. So, the output in Laplace domain is y of is equal to 1 by tau s plus 1 by s square. Then I break into partial fractions, and then you can get 1 by s square minus tau by s plus t s square by 2s plus 1. Now, once I have this one, I use inverse Laplace transform to formulate the output of y of t is equal to t minus tau into 1 minus e power minus t by tau. This is slightly interesting, because what we see here is the input is t, the output is t minus tau into 1 minus e power minus t by tau. The formulation here is slightly complicated compared to unit step. Now, if we analyze the error, the reference is t, output is t minus t into 1 minus. So, you get tau into 1 minus e power minus t by 2. So, this is our error signal. This tells us how good the system is. So, when time constant changes, error signal changes. Different systems will have different time constants. Now, if you look at the diagram here, the dotted line is the reference r of t, and the solid line gives you the output. So, you see that there is a constant delay between the input and the output. So, this is because of the constant changing input signal. Ramp is a very special signal, because ramp value changes all the time, is always increasing. So, the system should respond to the changes and then try to give the output. So, there is always a kind of delay in the ramp signals. This error tells us how good if the error is small, the system performance is good. If the error is large, the system is not good. So, reducing the time constant, if you reduce the time constant, if you are able to reduce the time constant, then you can improve the response of the system. So, once you model the system, I then analyze the response, and if I do not like the response, and then try to change the system constant, improve this one. This is what we call modeling. And the next stage is control, which we will study in the later part. So, in the modeling, we can always improve and make sure the system is good. So, there is a simple example here. So, it says that show that E steady state is equal to a t if r of is equal to a by s square. R of t is equal to a t u of t, r of is equal to a by s square. Take their input as r of t equal to a t u t, because r of s is given by a by s square. So, you take the input, apply to the system, y of is equal to 1 by tau s plus a by s square, and then you can get the inverse Laplace transform, calculate there. This is a very simple one, just for refreshing. So, you can try to analyze this one, and you will get the error as a tau is a constant error. The next one is unit impulse response. Impulse is so important in signal processing and a lot of digital systems, we always use impulse to generate response. For a control systems point of view, impulse response is so important because the transfer function is the impulse response of the system. If the input is an impulse, output is the transfer function. If you understand clearly, I have a transfer function here. When I have any impulse, the input is equal to 1 because the Laplace transform of impulse is equal to 1. So, what is my output? Y of s is equal to T of s. So, the Y of s is equal to T of s. When impulse becomes the input, transfer function becomes the output of the system. That means, if you want to do modeling or if you want to know about the characteristic, impulse response is the best. So, that is why impulse is very popular in control and signal processing applications. Now, if you actually take the transfer function here, y of is equal to 1 by 2 s plus 1, multiply the unit, that is R f is equal to 1, in the Laplace domain the impulse response is 1. So, the output is 1 by tau e power minus t by tau for t greater than 0. Now, if I plot it, I have this value. So, but impulse only lasts for this value, right? The other part is the output. So, if once you see that the error dynamic, this is the error dynamics. So, what is our error? Error signal is equal to R of t minus y of t, delta of t minus 1 by t e power minus t. So, the error signal is not that straightforward in time domain. Then the steady state error, when t tends to 0, e power minus t becomes 0 and delta does not have any value outside t equal to 0. So, what we have, the steady state error is also equal to 0. So, in this way we can actually also analyze the unit step response of the system. With the impulse response, we actually complete the analysis of basic test signals. So, in this class we learned about what is transient response and steady state response. We learned about basic test signals and we understood what is called performance. So, depending on the input, the output changes, and depending on the type of the input signal and also the characteristic of the system, the output will be different. So, when we are comparing two systems, we can actually provide the same test signals and analyze and compare two different systems. So, in the next class we will continue with the time domain analysis, where we actually will analyze standard second order systems. So, with this I would like to end the class. Thank you. This is end of week 4 part 3. Kamsahamnida.